The number e. If you've not heard of that number before, you're going to see a lot of it in the future. It's a number a lot like pi, where it has a decimal that goes on forever. And it also just happens to show up in nature quite often. Okay, in fact, it shows up so often that every basic scientific calculator has a button for e. All right, so this isn't a basic scientific calculator. It's more advanced, but it actually has two different buttons for e. The first is going to be over here. You're going to see e to the x power. If I press second, then that button, you're going to notice e to a power. Okay, most often, e is going to be the base to an exponent. So they've already got it set up for that. The other place that you could see it is going to be second division. Okay, it's going to be printed right up there. Okay, so if I type that in, you just get e. Okay, not e as a base, but you just get e. But it does represent the same thing. And in just a bit, we're going to figure out what that number is. There's two common approaches to generate the number e, both of which are going to use limits. The one that I'm going to show today is this one here. And the reason that I'm going to choose that one is because it looks a lot like compound interest. Okay, so think back to the equation for compound interest. What we would have is 1 plus a rate divided by n raised to the n times t power. Okay, so there's a couple of things that are missing from the compound interest formula. We don't have the rate and we also don't have the time, but we do have the n value in both of those two spots. Okay, and what we're going to do, sort of comparable to compound interest, is imagine what happens as n, the number of times you compound, goes to infinity. We're going to table that for just a little bit now, and what we're going to do is just look at this. Just look at this without the r value, without the t value, and what happens as n goes to infinity. What ends up being weird here is there's two things that kind of conflict with each other. As n gets big, as you plug in bigger and bigger n values, the base is going to get closer to 1. That's because this part right here, as n gets big, goes to 0. So you basically get 1. You're always going to have a little bit more than 1, but it is tending towards 0 in this spot, so it's going to get closer to 1. But as a contradiction to that, what you have is going to be raised to higher and higher powers, which is going to come back with higher and higher outputs. So we got one part that's attempting to shrink this down to 1. You have another part that's attempting to make this grow. Okay, so which one of these is going to take over? The truth is, in a way, they kind of balance themselves out and they end up at a certain value, which is called e. Okay, so we're going to investigate this by plugging in larger and larger numbers as we go along. Okay, now I have these written as exponents just because it's a little bit easier when you get down to here. But this is 10, this is 100, this is 1,000, 10,000, 100,000, and a million. Okay, so we're going to look at when n gets big, when it gets to a million. All right, so I already have the expression typed in. Of course, instead of using n, I'm going to use an x. Okay, and now what I'm going to do is go to the home screen, and I'm going to evaluate that for these values. Okay, I'm going to type alpha trace to pull up my function. That way I don't have to type it in every time. Go ahead and do open parentheses, type in 10, and we get that, which really doesn't look like much, right? We get 2.5937. By the way, what we typically do is use 4 decimals for this. Okay, so we got 2.5937. Okay, if we were to plug in 100, we get a little bit bigger of a number. We get 2.7048. Okay, 1,000. A little bit bigger. Okay, 2.7169. We'll go to 10,000. Just the tiniest bit larger. We'll do 100,000. Just slightly bigger. The only change is here. Okay, at the very end, we go from 1 to 3. Okay, and last, let's go ahead and do 1,000,000 and see that these don't really change. Okay, it's going to round to the same place. In other words, the limit of this is going to tend towards this number. Okay? As n increases, this expression appears to get closer and closer to 2.7183. All right, so the weird thing is that this number shows up a lot unexpectedly. Just as you're doing general mathematics, that tends to pop up a lot. So often that we gave it a special name, which is E, and that is going to be in honor of the guy who discovered it, which is Euler. And as an additional note, the function e to the x power, the exponential function with e as the base, is going to be referred to as the natural exponential function. All right, so e shows up in a lot of different application problems. The one that we're going to be looking at is compound interest, but we're going to call this continuous compound interest, because what we're going to be doing is thinking about compound interest as the number of times that we compound per year goes to infinity. So we move beyond quarterly, beyond monthly, beyond daily, beyond hourly. We're going to take it to infinity, the number of times that we compound. Okay, so what we're going to do is start with an expression that represents compound interest if it is compounded k times a year. Okay, the one thing that I've left out is the t. I don't actually have a t here. So we could think about this as an expression that would be for compound interest for 1 year. And then we could always add in the t if you wanted to do 2 years or 3 years or so on. Okay, so we can add that in later. And my goal here is going to be to take this and allow it to start to mimic the expression that produces e when you take the limit to infinity. Okay, so the math is going to be a little bit difficult as I go step by step, but in the end, it's going to simplify down to something really easy. Okay, so again, starting here, what I want to do is make this look like the expression that we were just looking at. So the big difference is that this has an r value where the other expression had a 1. Okay, so to resolve that, what I'm going to do is divide the numerator and the denominator by r. As long as I divide them by the same thing, everything is fair within that fraction. All right, so if I divide the numerator r by r, I'm going to get back 1. If I divide the denominator by r, I'm going to have to write that as k over r. Okay, so that's the justification to go from here to there. I'm going to divide both the numerator and the denominator by r. It doesn't look much better, but it does accomplish the first goal, which is to get a 1 here. Okay, my next goal here is going to be to make that denominator look like this exponent. Because if it does, then I can relate it to the number e. Okay, so to do that, what I need is to get k over r. Okay, I needed to match that. I need to divide the k by r. Okay, so I'm going to do that here, but in a sense of balancing it, what I need to do is then raise the whole thing to the r power. Okay, remember the power rule. If you have an exponent to an exponent, you can actually multiply to simplify. So if I've got k divided by r and multiply that by r, the r's would cancel and get me back to k. So this is a balancing act right here. Now what we've got is an expression here that mimics what we previously saw. 1 plus 1 over n to the n power, except that our n is k over r. Okay, but r is going to be a constant value. Okay, that'll be a constant. And if we think of k as like our n value going to infinity, then infinity over a constant value is infinity. And all of this could be represented as e. If we let k go to infinity, everything in here goes to e. But then you've got that one little extra thing, which is this exponent. And that's it. If we let k go to infinity, it will simplify down to e to the r power. All right, so for continuous compound interest, that is when the number of times you compound is infinite, it can be said that e to the r power is the factor applied to the principal. Okay, because this is going to take the place of our compound interest formula without the principal in front. So this will be the factor applied to that principal. Okay, now the one thing that we left out was time. We didn't actually have time here. Okay, so if I want to calculate the balance of an account that's compounded continuously for t years, it's going to be the principal times e to the r power raised to the t power. And then again, remember the power rule. If you have an exponent to an exponent, you can actually just multiply them together. So we can rewrite this as p of t is equal to p times e to the RT power. You don't have to show it as exponent to exponent. You can actually show it as the product of those exponents. Example 1, and our only example here. $15,000 is invested at 8%, annually compounded, continuously. That's important there, continuously. What is the balance at 2 months? All right, because it says continuously, we're going to be using this formula, okay? So P of t is going to be equal to P times e to the RT power. Okay, we're going to be looking at 2 months, but t is measured in years. So 2 months out of a year, 2 months is going to be equal to 1/6 of a year. So our input is going to be 1/6. We got P of 1/6 is going to be equal to P, the initial principal, which is going to be the $15,000, times E, and E is just a number, okay, times E to the RT power. R is the 8%, and T is 1/6. And that's it. If we type that into the calculator, we will get the balance after 2 months as described here. 15,000. We're going to press second this button, so it brings up e to a power. And again, every basic scientific calculator can do this. Okay, our exponent is going to be 0.08 times 1 divided by 6. And that's your balance.
Later, blah.